Wanted to take a minute and put together a nice example of the secant method in MATLAB. Well, at least I hope it's nice. I've gone ahead and used an anonymous function to define a reusable objective function in one line. So the variable feval is actually a function name that we can call over and over because it has the handle operator right after equals. The independent variable is b, and that's the nonlinear function we'll actually be solving. So b cubed minus 100 times sine b. Now I did go ahead and check, and this does have a few zero crossings. I had to change the function around just a few times, finding something that does actually have roots. And to make this a bit easier to check, I went ahead and did this simple plotting function. So xp and yp is for xplot and yplot, an array that I made. And I had to actually go out and find a function I didn't know existed in MATLAB preceding this to make my life a little bit easier. So xp, not xp points like video games or whatever, but xp goes from negative 20 to positive 20 in steps of 0.1. So a decent resolution going from a widely negative range to pretty positive range, and that's the area I expect the zero crossings to be in. Array fun is actually meaning array functions, and that allows you to send an entire array's worth of data to a function one piece at a time. If I just typed in feval and sent it all of xp, it would not work. It would send xp as an array, and that function evaluation form is not ready to accept an entire array. It would try to cube the array, and it sends me mathematical errors because MATLAB by default employs matrix math. You want it to send one number at a time and call the function repeatedly. I guess whatever that would be, a range of 40 at 0.1, so that'd be 400 times. I didn't feel like writing my own custom loop to send it one at a time. It would just take extra lines of code. So that's the nice thing. It's a convenience in MATLAB that some of these functions exist. Array fun makes it easy. And then next, I just plot xp versus yp, so we can actually see what this function looks like. So stop talking and show me. Press F5 to evaluate that. And if I can bring the functional window back up to the front, this is what we're looking at in terms of the objective function. Now, consider this, you might call it unknown information. Whenever you're doing numerics problems, like I personally could not visualize with any reasonable accuracy b cubed minus 100 sine b. I knew it would be a little bit squiggly because of the sine function. I knew it would have a cubic overall shape because of b cubed. And yeah, that's what we eventually got, but as far as where every point lines up, who knows? Now you can graphically go in here and determine the zeros. If you use the zoom in function, MATLAB has a nice little window here you can set up. You can just keep zooming in, doing slices right around 0. And now we're getting into the part where we can actually really start seeing where they're going to be. So it crosses 0 at just a little bit less than negative 3, crosses 0 at 0, and crosses 0 at a little bit less than positive 3. It looks to be symmetric, which makes sense when you look at the evaluation of the function. Let's right click, reset to original view. We're back to that the overall viewpoint. One other thing that's nice about MATLAB, you can click this button up here, and that is the data cursor. You can actually click on your functions and pull out data points. As far as I'm aware, you can only pull them out where you actually have functional evaluations. I do not believe this cursor does interpolation, though I may be mistaken in the most recent versions of MATLAB. You see it kind of snaps between all those 0.1s. In fact, look at the x coordinates. It's only going to values of 0.1 because that's where we evaluated the function. So this is a nice and concise way to reference this objective function. That's what we're wanting to find the zeros of repeatedly. In fact, we just called it 400 times and plotted it with a whole total of 4 lines of code. You'll notice I put a pause in here in the function, and that's a nice handy tool in MATLAB because now if I press spacebar, we're going to go down to the rest of this code. Before we proceed graphically though, let's go over what I'm actually doing. I said this was an example of the secant method, so it better be that. I start with 2 initialization points. We need 2 in the secant method because we're going to find essentially the slope through those 2 points and project it down to our goal of 0 functional value. We want f of y equal to 0 to be the successful solution. So my first guess is 5 and the second guess is 7. If I want to change those right now, I have to go here into the code, change it. If this is just for me to use, that's not a problem, but if this is a published code, that would be trash. This is a quick example. Nothing I'm making elegant at all. So just for the sake of tracking the movement and evaluation of these search locations, I am making a different array of information called track 1, track 2, where those will be the functional values of x1, x2, xn. So in the end, see I've already built it down here, I'm going to plot all of the x values that were checked on the way to a solution. I'm going to plot those against the functional outputs as you're moving towards a solution. They'll all be plotted with little plus cursors. So as far as secant method goes, that's everything. In fact, the pause line, the track line, and the plot line are unnecessary. So the entire secant method is held here within really just 2 lines of code. It's very, very nice, very concise, works wonderfully. So you heard me reference this pause function. That's where the code is at right now. It's waiting right there, and all I have to do is go up here, press any key, and it proceeds. So I've not muted hardly anything in this code. So right now you see it just evaluated the x1 equals 5, x2 equals 7. You can see that in the x array here. I is presently equal to a value of 2 to handle the initialization properly. So it's now going to start going into the loop. It just hit the for statement and paused now at that line. So it's waiting for me to press the key again. You wouldn't do that if you're trying to find a quick example. I'm just doing that for you, for an example to students. Press spacebar again, and now we see the plot is generated and we have some new data. So with our 2 initial points of 5 and 7, those had functional evaluations of 2.2 in the y-axis and 2.77 in the y-axis. In fact, this is 220 and 277. I can't forget about the scaling right there. I should actually run this whole thing again here in a minute, having changed the default display. In fact, whatever, let's do it right in the middle of the problem. So short, let's do short G. Okay. So that should change the visual style halfway through. Maybe I just caused a big problem. We'll find out. So in the graph, you see that we have 3 points actually. So one's hidden up here on the very right-hand side. But we have our initialization points at 5 and 7. It executed the functional values and drew a secant line straight through those, trying to find where 0 was. It was close, but it did the functional evaluation and missed by just a little bit. So that means the third point actually had a value of 7.77 going by our scaling factor here. So this is 1 times e to the second, so that move it over 2 spots. 7.77 off of 0. So close, but not quite. So let's let the system iterate again. Press spacebar. Now we're at I equals 4. All the previous data is still there for us to view, but now we are at an x value of negative 3.115. And then in a y value, I guess it didn't change the format mid-program anyway, a y value of negative 27. So actually the y value is worse, but we'll see if this works. So 0.1, 0.2, 0.3, 0.4. Okay. So we're still moving away. Let's see what 0.5 does. Okay, so it's come a little bit back in the x-axis, and now we're actually a lot closer to 0. Look at that, 0.00254. So that's actually 0.2 away. That's the closest point we've had yet. So graphically, you can see we're starting to cluster in around this 0 location there, which, if you remember, we had a 0 pretty close to negative 3, so this seems to be working. Let's go ahead and press spacebar 2 more times. That's the maximum count I've let this program do. I didn't install any convergence criteria because I figured I would program that in while you were watching. And let's go ahead and zoom in this region down here where everything seems to be converging. So it seemed to iterate down and closer, and yeah, so we're looking at 2.8962. And in fact, if you look at the progression, so x started at 5 and 7, then negative 2.83, negative 3.11, negative 289, 2.89614, and then of course it goes to the next row, negative 2.89620388, and these y outputs are getting very, very close to 0. So let's get rid of the pause and just throw some more computational time at it. Let it go 50 iterations. Now this is going to put out a lot more data than we ever really want to look through, but we would expect to see track go down very near 0. I mean, we're already down to, how many sig figs is that? That's 7 digits of zeros. So that's extraordinarily accurate. And we're changing very, very little in the x dimension, but let's just show you what happens when you throw a lot of computational time to it. I'll take all these extra spaces out. I think the pauses are gone, so let's just Good, I broke it. That's wonderful. It hits probably the machine limit, or at least the MATLAB limit, so 2e to the negative 14th. That's great. So maybe instead of 50, let's just do 10. Okay, so yeah, in the 9th iteration, it actually starts hitting such small functional values that it's not changing anymore, and it can't represent numbers smaller than what you're looking at here. So that's actually, for all intents and purposes, 0 in MATLAB. So both the x value, negative 2.8962, and oh, notice now it updates to the short g. Let's actually go long g. There we go. Negative 2.89620386. So it is not changing all the way down to 4, 8, 9 significant digits. 209. Wow, all of the digits are exactly the same as the previous iteration. So I think we overkilled it. But what's interesting is it only took 11 steps to get there. 2 of them were total guess. So 9 improved steps, and it's completely solved a nonlinear function. That's pretty nifty. But now we need to acknowledge that we have hard-coded this convergence. It may take other functions much more than 9 steps to find that, so let's actually take this to allow it to go up to 20, because I want to set a ceiling. If you use a while loop in place of a for, it opens up the possibility of a divergent solution, which can happen, putting your computer in an infinite loop. And that's obviously undesired. So if you put some ceiling on this, say 200 or something that's still relatively small for a computer, that's not going to take hours for it to crunch through, then you at least protect yourself from those runaway loops. So let's take the plot out of the interior loop. That's going to take a lot of extra time we don't need to mess with. Still doing the iteration, but now we want to set a convergence criteria. So if almost all convergence criterions start with an if statement, if x of I plus 1. So basically the new x that you just calculated here in line 17, if the distance, but we want to look at the distance between x of I plus 1 and x of I, minus x of I, then we want the absolute value, because I don't really care which direction it is. The absolute value of that is less than 0.001. Then I want you to break the for loop. And that's the only condition we really need to set. I probably made some sort of programming mistake here, but we'll see how it goes. So really this should be met pretty early. So if we look at our x progression, the first time it changes less than 1,000th of a unit, it will stop. So 5, 7, 7 to negative 2, that's more. Negative 2 to negative 3, that's exceeding. Negative 3 to negative 2894. So that gap is no good, but 2894 to 2896, still too big. 2896 to 2896, there it is. So we should see 1, 2, 3, 4, 5, 6, and on the 7th it will stop because it did not experience a change larger than our convergence criteria. So I've set myself up for quite the goal here. Let's see if it works. Good, that's fun. All right, attempted to access x4, index out of bounds because number x equals 3. That's fun, line 21. But it just said it. Oh, we did this after the increment, so we need to put the increment after our functional evaluation. Think that was my mistake? Hey, it is. All right. Look, fixed it. So as we expected, negative 2.896 satisfied the convergence criterion, and it broke. In fact, we could even put an output here. There we go. So it actually specifies you reach the convergence criterion whenever that finishes up. So that is a simple example of the secant method. All the stuff initially, except for the setup of the feval, you could comment out all of this. In fact, that'll be fun. I'll comment out all the unnecessary things and show you how concise this could actually be Let's see, your tracking is gone. Let's leave the convergence in. Well, that step's unnecessary. If you really want to be fancy, you can just put it all in one line. It's not really fancy, it's just syntax. Yeah, the iteration scheme is necessary, and the plot is just extra at the end, but that should still function. Good, I broke it. Error secant method 28. Plots, track, plus, what? Oh, yeah, because I never defined track. All right, I commented it out. There we go. That still finds the correct answer. We don't need any plots, so really it takes a functional definition line, 3 lines of setup for the iteration, a loop with one actual... That's the meat of it. That is the update equation. That's equation 326, and that does all the work. And this only takes 7 iterations to reach an accuracy of 1,000th. If you want to make that a 10,000th or 100,000th, there you go. And now it might take a whole 8. So it's a very effective method to finding solutions to nonlinear equations in short periods of time. I'm going to leave those mistakes in that I made during this example because people are people. We all make mistakes. You don't feel bad about yours, and I'll leave a few of mine in the video. There we go. Hope that helps you understand.